Alright, today we're going to do a very quick scalar versus vector video. This is from one of the extra help sheets. And to start us off, I'd like to hit the bottom half of this, basically characterizing what is scalar, what is vector, and then we'll work on scalars and vectors getting added together, or basically vectors getting added together in the same direction or opposite directions. Okay. So starting off with this bottom segment, characterized by magnitude only is going to be a scalar. Once we throw magnitude and direction, we are talking vector. Distance is only a number. It's only a distance. So we're going to talk about a scalar. Velocity is actually going to be speed with a direction. So we're talking vector. 8 meters per second is simply a speed because we are only talking about a number with a unit. So that guy is scalar. Speed itself does not have direction. I can be moving 8 meters per second forward, backward, side to side. It does not matter. It's simply a scalar. Displacement is essentially going to be the total distance from where you started to where you moved in a direction. And when we start doing the vector addition, as we'll do up here, you'll see displacement is going to be what our end goal generally is. So that's going to be a vector. 4 meters east, the east gives us a direction, so we know that's a vector. 3 miles south, again a number and a direction, that's a vector. And 55 kilometers per hour is definitely going to be a scalar. So, scalars are simply going to be numbers. We do those whenever we use the equations, speed equals distance divided by time, stuff like that. You've been using those all week in class. The vectors are what we can actually start adding arrows to and creating drawings. So we're going to practice 2 of them real quick, and then we will call it a day. Anyways, tennis ball is thrown 11 meters north towards the wall. 11 meters north. Bounces off the wall and travels 17 meters back south. So we're going to figure out what's the final displacement. And I wish I'd have drawn myself and left a little more room. So we're just going to draw through this next problem. And we're going to call that 17 meters. So what's my total displacement? Well, I started here and I end all the way down here. So my total displacement is 11 minus 17. So we're going to end up with a number that happens to be 6 meters, but it's in the negative direction. Okay, so 6 meters south. South. Now you don't have to write the south, but you get the idea. In terms of our second problem here, Jason decides to go for a drive. He drives his car 8 miles south for 10 minutes, then turns around, drives 11 miles for another 15 minutes. Draw the vectors head to tail and calculate the resultant's vector's displacement. So knowing that we're dealing with displacement, do I care about the 8 miles south, the 10 minutes, the 11 miles north, or the 15 minutes? Which of those matter and which of those don't? Well, if this had said calculate the resultant vector's velocity, I might care about the 15 minutes, and I might care about the 10 minutes. Actually, I really would. But since it says just displacement, all I'm worried about in this case is the miles south and the miles north. So, in this case, we go 8 miles south, 8 miles, and then turn around and travel 11 miles north. 11 miles north. And so our displacement is going to be that 8 and then 11 in the opposite direction. So we're going to end up with that guy and 3 meters. 11 minus 8. So our displacement is going to be 3 meters north. Okay. Hopefully this is stuff that makes sense. If it's not, obviously we can talk before or after class, but this should be very, very doable.